So in the previous part, we talked about the disadvantage of having workers initialized with one random stream, and that it can lead to non-reproducibility when you evaluate functions in load balancing manner, or if you use clusters of different sizes. So I'm going to talk, in this part, I'm going to talk about two packages, SnowFT and for each. The SnowFT, full disclosure, I wrote it with Tony Rossini a couple of years ago. And basically our goal, one of the goals that we had was to solve the drawbacks that of the reproducibility and then add other features as well. So the solution here, the idea behind it is, instead of associating one stream per node, to associate one stream per task. Oh, I'm sorry, I forgot. I have a new helper here, Kirill. So if you need help, and then Patricia is over there. Is Adela there? Adela is coming too. So please make yourself visible if you need help here. So one stream per task. So everybody, so as in this picture, you see each color is one random number stream. So each task is carrying its kind of stream with them, and therefore it doesn't matter on which node it's evaluated. It doesn't matter what's the size of the cluster. It will be always reproducible. Okay, this is the part that is not going to work in RStudio, unfortunately, because there's a bug. If you are interested in details of the bug, there is a link from the website. You can click on it. I asked them to solve it before this tutorial. They didn't, so. So either you use different RUI or you just watch how it's your choice. As I said, it's an opportunity to learn something new for those who are only used to RStudio. All right, so in addition to the random number streams, there is a simplification of using the cluster or the snow system that I talked about. And the simplification is that you only need one function and it does everything. So in useR, if you load library SnowFT, and you set your seed, and the main function of the package is called perform parallel. So you do perform parallel. You are passing the size of your cluster, so P, if you have it still in your environment, if you don't set it to a number of cores that you have. Then we will pass the r.sequence. This is the sequence that generates the different loads. Our function will be rnmean. That's what we did in the last step. We will pass the seed that we just set. And we also say what type of cluster we want. So the argument is called CL type, and it will be a socket sock, for the reason I talked before. So that run, and if you look at the tail of, again, it returns result as cluster apply. So it will return list as cluster apply. So I unlist it. So these are means of random numbers with zero mean. What happened within this function? Basically, the following steps. So cluster was created of the size P. That would be the make cluster function, right? Each node was initialized with the Lecuyer generator. Then given function was performed on the cluster in a load balancing manner. Cluster was stopped and the result returned. So all the steps that we did explicitly are now in this one function included. As I said, since the tasks are now carrying the streams with them. It doesn't matter what the size of the cluster is. So for example, in this loop that I'm going to now just copy, and what I will do, I will iterate over different number of nodes from 2 to 4, and I will do the perform parallel with this different number of nodes and just generate random numbers. So I will copy this. Okay, so the first vector, so they were like 2, 3, and 4 size of cluster, and in all cases, we are getting the same results. And as I said, it's in load balancing manner. If you want to preload libraries or initialized workers, the task that I talked about in the parallel example, when you use cluster eval q, in this case, since you are not dealing with the cluster explicitly, the cluster is created inside of this perform parallel. You just pass it as arguments, the thing that you need. So my RD norm, we have that function in memory. Yes, it generates RD norm, or it generates random numbers from a discrete distribution from extra distr, and we will set mean is 20 and SD is 10. And then what you do is perform parallel. You are passing the number of nodes, P in my case. Okay, I have to put it a little bit. I will generate 1,000 random numbers 100 times. The function is my RD norm that I'm passing. I will set the seed, CL type, oh, okay. So the analogous to the cluster eval q that we talked about in this case is init expression or init exper argument for passing expression to the workers, init expression, and we will say library extra distr. So it will load the library on all workers prior to any computation. And for exporting objects from master to workers, you will use the argument export. And the same way as in parallel, you pass a vector with the names of the objects you want to export, mean and SD in this case. Okay, when I look histogram of the results, there it is. So mean 20 and standard deviation 10. So we got some results. Okay, so basically the change here is that you don't do everything explicitly. You pass everything into one function, and it does these things for you. And this, what the last call that we did would be equivalent to, maybe I'm not going to run it now, but basically you put, instead of export this, you would pass everything into its expression, the same way we did last time with the cluster eval q, to pass objects from master to workers. So in all the cases, we use the CL type is sock. For some of you, it might be the default, but basically the default is, it looks if MPI is installed on your computer, and if it is, it uses MPI as default. And you can determine what default you are using by using this get cluster option dot type from the snow package. So if you do get cluster option type, there are various options that you can set. For me, it's SOC, but you could be, in your case, it could be different ones. So if it's not SOC in your case, you can use the second line here to set it to be the default. So if you use the set default cluster options, you want to use the type SOC, then run this one to set it to default. And in such a case, you can always eliminate this argument. It will always use the CL type as SOC, okay, to use the socket cluster. One fun feature of this is that it can actually resize the cluster while it's computing. So, for example, if you start the run during the day and your departmental cluster is full and you want to make space for other people, so you set a small number of nodes, but then in the evening maybe there is more free, so you can expand it to more workers and then put it back again maybe in the morning. And this is kind of done in a simpler way that the master writes the size of the cluster into a file. It's called .cluster size. And it also reads the file while it's computing, and reads the file if it changed. So if you just change this text file to some other number, then it will change the size of the cluster. It reads it in its waiting time. So I'm going to try it now here. So I'm going to start. This is a relatively long, a couple of seconds computation, and while I'm running it, and I will start it on 2 nodes, and while I'm running it, I try to change it. So I'll try to change the size of the cluster. So I will copy this, and I'm also, Perform Parallel does have this monitoring of the time integrated, so you can use the snow time function without any tricks that I showed you before. You can just do snow time, and it will show you the plot that we looked at. So I will do this, and then here I will open the cluster size file, which has 2 in it, and I will change it to 4 and save it. And maybe now I change it to 3. Let's see if it ended already. Not yet. Well, let's change it to 2 again. Now it's done. So let's plot the TM. There we go. So I started with 2, then I switched to 4, then I reduced it to 3, and then to 2 again, and at that time it was already the end. So you can change the cluster size dynamically with this. Any questions so far? Yes?
Significant difference between MPI and SOC in the performance?
In the performance, I think that MPI probably is more efficient, but I never done any measurements or anything, and I never done a comparison. No, I don't know. Does anybody have experience with MPI? Another useful thing that SnowFT can do is that you can actually run a program sequentially with the same command, with the same random numbers, and it will give you exactly the same results as when you run it on a cluster. And this might be useful especially for debugging, because debugging parallel program is not that straightforward. So if you just want to run it sequentially, make your code like debug it, make it bug free and optimize it, and then you can run it in parallel with the same function call. So I will unlist the result, perform parallel. And for running it sequentially, you would use 0 for the size of the cluster. So you would put 0. And here I will just generate 5 random numbers 3 times with R norm. I set the seed. And ft underscore verbose will give you some extra information about the cluster, so you can set it to true. And in this case, it will tell me that it runs sequentially, that initialize the RNG, and the results. If you do the same, I'm using the same call with just setting the cluster size to 3. And it will tell me that now it runs on a socket cluster size 3, which host it's running, and the results. And if you would compare the results, they are the same. Any questions on SRFT? Hmm?
This trip as changing the cluster size to this one, is it possible we can do it in the snow package or not just related to this one?
To change the cluster size? No, and the reason is because in Snow or Parallel, the master actually, it just waits for the results and doesn't do anything. And in fact, this is the reason why it's not working in RStudio, because that function, this blocking and unblocking receive, it's not working in RStudio. But in Snow, the master just blocks and waits until the results come. In SnowFT, it looks at the results. If not, look if the cluster size changed and do something, if it changed. So it does something while it's waiting for its results in its waiting time. Yeah. Any other question? Okay. So that was SnowFT for each. It is very, very nice package developed by Clave and Weston. I think they were Revolution Analytics when they wrote it. Now, I believe Microsoft. Okay, and the idea of the for each package that they provide an alternative looping construct, and the looping construct can be then used either for sequential or parallel computing, independent of the backend, parallel backend. So let's load the library. This will work again in RStudio if you want to use it. So I load the library. I create a sequence of numbers. I will sample from 1 to 1,000 10 times. Okay, what did I do? And sequence equals. And then I will assign the result to res, and I do for each. And now you put, it's a little bit like for, for loop, and you pass over which sequence we iterate. And so we say n is n sequence. And then you do percent, and what function? So R norm with argument n. So whatever you assign here, the argument n here is passed to here, and this gets, the n sequence gets segmented and set to the workers, similarly as we did before. So what did we get back? Class of res is list of length 10. So our n sequence is of length 10, and again, we got one result per task. What's the length of the first element is this. So if I look ahead n sequence, so n sequence has 476, so it generated first worker generated 476 random numbers, and that's what we got in the result. So it returns a list as we had with cluster apply and perform parallel. However, you can, in the for each loop, you can define how these results are combined together. So you don't need to do explicitly afterwards. So if we do for each, n is n sequence, and so this will be additional argument, and the argument is called dot combine. And the dot combine argument, you are saying what function should be used to combine the resulting elements. So if you put C, it means it's going to be vectorized. And do R norm n. So now length of res, instead of 10, it's now all the random numbers together, right? Because it was all put into a vector with the combine. So you can put any function into the combine. For example, you can put things into matrix. By the way, everything what we do now, it runs sequentially. And how it runs in parallel, I'm going to tell you in a moment, okay? Everything works sequentially right now. So for each, so let's put something regular when we want to put it into a matrix. So we will generate 100 random numbers 10 times. And we will do combine R bind. Remember, we use the do call R bind for putting the results into matrix. Now we can just do combine R bind. And do percent R norm n, and dimension of the result is now 10 times 100, so it was combined together with R bind. You can combine it not just like manipulation function, but you can use aggregation function. For example, plus is the next example. If you use plus, it will length of res is 100. So in this case, all the rows that we had here in the previous case, all the 10 rows will be summed together. Also, if you have a sequence that you want to segment, multiple sequences that you want to send to segment it to the workers, as we did with parallel case, it was the cluster map function that we used. Here you can do it in the for each loop. So res as for each, n is, I repeat, 10 5 times. So n is passed. And then I will also use different mean. So let's say 1 to 5. I have here power to 2. Power to 2. So that's passed, and combine R bind and do R norm, and I'm passing the n, and I'm also passing the m as the argument mean. And what happens is that the m gets segmented also, just like the n argument, okay? And so different worker, different task is computed with different mean. So our res is then a matrix with 5 rows, and as you can see, each of the rows has different mean. Okay, so as I said, all this happens sequentially, but the nice thing about for each is that now you can define a parallel backend. And the parallel backend, there are a couple of them available. Here's the list. So do parallel backend. The parallel backends are defined in contributed packages. So do parallel package, it uses the snow functionality of the parallel package, what we just handled in the first half. Then there's a doMC, which uses the multi-core functionality, which, as I said before, works on single computer only and not on Windows. Then there is doMPI, which uses RMPI, and then there are others like doFuture, doRedis, doAzure Parallel, and you can, you can come up probably with your own package if you want to. They do all kinds of different. But the good thing about this is that regardless what backend you use, the for each has the same syntax, right? So we are going to use now doParallel. So let's load that library. Library doParallel. For the doParallel backend, we need to create a cluster, just like we did in the Parallel package. So CL is make cluster, and size, I'm going to say 3. You can say whatever you want. So I have a cluster of size 3. And then what you need to do is you need to register that backend. So you do register doParallel, and you pass the cluster. So you probably, there are different, when you're registering different backends, you probably have different types of arguments that you put in. But when you register a backend, your for each construct is the same, almost the same as the sequential. So I'm going to now use the same for each that I did before. The only change before the sequential and parallel is that instead of do, you pass there doPar for doParallel. That's the only change you have to do from sequential to parallel. So you run it, and it runs in parallel. We don't really know, but it's supposed to run in parallel. It doesn't have this plotting functionality, so we cannot look, but we believe that it runs parallel. Okay, there are some, you can get some information about the workers. For example, you can use function get do par workers 3, so I have cluster of 3, and get do par name gives you, it's telling that the backend is doParallel, and it's the snow functionality of doParallel. Okay, as it was in the case of the SnowFT and the Parallel package, we can initialize workers, in this case with extra argument. So I will set a mean to 20 and SD to 10, and my RD norm, I probably have it still in memory, my RD norm function that we used before. Yes, I have the right one. And then the loop, so function that we actually used with the SnowFT and Parallel package, we are going to use now with for each. And we say our replicates will be 1,000, 100 times. We will combine it with C, we'll combine it into vector. So combine is C. And there is a function, argument called .packages that you can use to initialize workers with packages. So it's a vector of packages name. So extra distr, and then we do percent do par percent my RD norm and passing R. So this worked. Theoretically, well, there is also an argument called .export that allows you to export objects from master to workers. So you can use that. So histogram res. Okay. So as you see, we don't need to actually unlist anything because we combine it to a vector, and then we have our random numbers. that we wanted with mean 10. All right. So that's the for each in parallel. Now for the random numbers that are reproducibility in the for each package. So results are not reproducible out of the box. So when you set a seed, set seed 1, and you do for each, n will be, I want 2 numbers 5 times. I do dot combine R bind matrix and do par, run it in parallel R norm, n, n. So I run this, so I get these random numbers. I do this again, set seed, and again for each, and I get different random numbers. So we have the same situation that we had in the previous cases. So out of the box, the workers are not assigned, are not using random number streams, and that's implemented in the do RNG package. So you have to, in order to have reproducible results, you load the library do RNG, and this one can initialize the workers or streams, can use the random number streams of the useR generator. Sorry. And the change, what you do here is that I set a seed, and I use the previous function, but instead of do par, you will do RNG. Okay, this thing, it also returns some state of random number generator. So I will just assign the result to res1. And I do the same thing, set seed, and again do the same thing and assign it to res2. And are these identical? res1 and res2, yeah. Oh, okay, what did I do wrong? Oh, I did the for each again without setting the random number seed, because first I run it and then I run it again without setting the number. So let's do it again. Set seed, res1, set seed, res2, there, and are they identical? True. So if you set the seed and you do the do RNG, they are identical, whereas before they weren't, when we just used the do par without the do RNG. There could be a case when a package that you want to use is using internally for each, and it's using do par without the random number generator. So can you make it reproducible? Yes, you can, because you can register. You can do it by registering the generator and then just use do par. So if you do register do RNG with the seed, and then I will put it to res3 now, the result, and instead of do RNG, do par. And if you do it again, and res4, I think this would be the same as set seed. So are they identical? res3 and res4? Yes, they are. So if you register, you can use do par, and this could be helpful in cases when you use other people's code who actually don't use the do RNG. Similarly to SnowFT case, you can run sequential code. You can reproduce the same numbers with sequential code and of cluster of different sizes. So you register with when you want to run code sequentially with these random number streams, then, because if you just want to run it sequentially, you do this do instead of do par. But if you want to use the task the same random numbers, then you have to do register do sequence to SEQ. So you are registering sequential backhand, right? Then you do set seed 1, and you can do your for each the same way. I suppose you have to do RNG here, RNG and rest sequence. And is it identical to the other results? Rest1 to rest sequence. Yes, it is. So if you would just use do, it would not be identical because it does not use the Lecoyer's random number generator. But if you do want to make it reproducible, you use this sequential backhand. Okay, any questions for each? Yes?
For each neural apply can be used for the same jobs. And what would you recommend for what? When would you use for each and when would you use parallel apply?
You know, I'm biased. I cannot give you a recommendation because I authored the SnowFT package. So, but I like the for each because it has these various backhands and they are still new, being developed and so on. It's a different syntax, different ways of writing. I think it's just it's up to each, everyone. They kind of do the same thing, except that when you want to use some parallel backhand that the SnowFT doesn't have. I don't know. It's a matter of taste, I suppose. All right. Yes? Okay, go ahead.
If you use for each with do RNG to get back the random numbers which were used, is it also possible to get this back to use cluster apply or something?
To get the status of the random number generator? I think what you have to do is then you send a call to the workers to give you the status for each worker. But SnowFT will be more difficult because you have each task is in different state. Yeah, it's I will have to think of it more. But yes, for parallel, you can send a command to the workers. Give me a state of the random number generator. Yeah. Those other questions, Sandra? Yeah.
I haven't fully understood what is register. These different commands to register.
Yeah. So basically, the idea is, in order to use the same syntax for all the backhands, then the idea is that you register one backhand like the do parallel. You could have registered do MC or other backhands. You register it and then you use the same construct of the for each, and it's just using in the background, different methods for dealing with the parallel processing. Yes, that you have the same syntax. Yeah. Any other questions? Okay. So benchmarking is the next part of this, and basically as you can think that with parallel processing, there is always some overhead with the computation. You have to create the cluster, you have to send the messages, get the messages back, and so on. And usually computations of like simple computations like we did with the R norm and everything, it's very fast. So usually for such computation, it would actually not be worth it to do it in parallel. So you have to always think of, is it worth to run it in parallel or not, if it's faster to run it sequentially. Also important thing is too that you optimize your code before you start to parallelize to actually make the sequential code efficient. It is also important to have an idea about the possible speedups in the particular applications. You know, how the code speed up on how many nodes, because at some point you might not get any speed up, as we will see in a moment. And there are a couple of ways to measure runtime with R, and we will use the system.time function, and we will use an example of Bootstrap that I modified slightly from the do parallel vignette. So we will use, so the Bootstrap function is in this code segment. You can copy it for the Bootstrap function and paste it into R, and then if you call Bootstrap, well, maybe I should say what it does. Basically what it does is it takes the iris data set and it samples from that data set 100 rows with replacement, and it runs the GLM functions on that sample data with binomial model, and it returns coefficients. So as you see this sample here, it's this will be different every time you run it. So if you run the Bootstrap, okay, it's saying it will give me some warnings about it did not converge, but that's okay for this purpose. And as you can see, every time you run it, it gives different results. Sometimes it converges, sometimes not, but for this as a toy example, it's okay. Now, this next segment, basically, I put for every method that we learned about today, I put a function that evaluates this Bootstrap in parallel. And you can use this code as an example of how you can see the differences between the different methods, how you actually define it and call. So for example, in the parallel case with the parallel package, the function is dependent on you are passing how many nodes, on how many clusters you want to run it, how many trials, meaning how many times we will run the Bootstrap function, and the seed. So what in this case, you make the cluster, you export the data frame to the workers, you set the seed, and you call cluster apply with 1 to n trials and the function Bootstrap. And then you stop the cluster and you bind the results together. So that's the parallel. The next one is the load balancing one, which is exactly the same, except that cluster apply uses cluster apply LB. SnowFT, as we talked about, you can use just one function that does everything. That's this call. And for each case, you create the cluster, you register the parallel backend, register the random number seed, and do the for each loop, and you export the data frame and the Bootstrap function and call it. And stop the cluster and return the results. So 4 functions, and you might just copy it and paste it. Okay, so example, if you run the SnowFT, run.snowft, and first argument is number of nodes, so I said run it on 3 nodes and 10 times, then I get these results. I run it again on 4 nodes, and I get exactly the same result. So these are reproducible, and the same if you do run dot for each on 4 nodes, I get these. Say now on 5 nodes, I get these results. Again, they are the same. So snowft for each reproducible, but if you do run.parallel on 3 nodes with 10 and 4 nodes, some of them will be the same, but some of them are not, so they are not reproducible. And this is using the cluster apply, and the reason, as we talked about, is that the clusters of different size. Okay, the next code is actually is looping over the methods and over different number of nodes, and calls these functions. So I'm going to copy this, and it also run it sequentially for comparison. The last, no, not the last, but the function for plotting results segment just is a function that plots the results that you will see in a moment. So it basically takes the runtime and uses ggplot to plot runtime for different methods dependent on different number of nodes. All right, so we can run it now. The runtime function has the first argument is number of trials. So number of trials, and the second one is on how many nodes it should run. So let's run it. Runtime. So I want 50 trials on 1 to 4 nodes, 1 for sequential, and then to 4 nodes. So it runs for 2 nodes, 3 nodes, okay, and show runtime. That's the function that generates the plot for the T. There we go. I also added this purple line is linear speed up. This is something you would expect in an ideal case. And what do we see? That all the methods actually increase runtime. So the first one, x-axis, is the number of nodes, and the first one is sequential runtime. And so as you add number of nodes, it actually adds runtime. And this is the case that I talked about, that if you have a very short computation, it will take longer time to run it in parallel than sequential, because you need the time for all the management of the cluster. However, if you run this many times than just 50 times, and this might take a little bit more time. Maybe we can run it and see if there are any questions about it. So I will run it now. Instead of 50 times, I'm running 1,000 times. I will call the bootstrap for, let's see, sequential, 2 nodes, 4 nodes, and 6 nodes. Okay. So this will take some time. Are there any questions? So we can use the time when it runs. Okay, first, so 2 nodes. As you can see, parallel LB is more efficient than parallel for the load balancing stuff. snowft is a little bit doing a little bit worse than for each. And both for each and snowft is somewhat worse than parallel and parallel NB, and the reason is because it's a layer on top of parallel. All right, so let's look at the plot. Show runtime T. So this looks better, right? This looks, so we have still the purple is a linear speed up. And as you can see, all the methods decrease runtime with 2 nodes. It still decreases runtime with 4 nodes, but it increases the runtime with 6 nodes. And as you saw in my case, I have only 4 physical cores on my computer. So when I do 6, it increases the runtime. We can look under the hood what's going on in this case with this application, and we will use again the Snow library for that. Library Snow, and I will do st is snow.time, and I will call the run.parallel lb function on 6 nodes, 1,000 times. Okay. And plot it. Okay. Now you can kind of see what's going on here. So this is using the parallel cluster apply LB function, and as you can see, the master needs half of the time for creating the cluster here, and then the computations are very short, and so lots of time sending messages. So here you can see why we actually increase the runtime when we run it in parallel. Okay, so this is kind of important that you have idea in your application how much time these things actually need. I show here a plot. So these computations were actually very short. I used our departmental Linux cluster with 14 nodes, and I ran this that I modified slightly so that the bootstrap takes longer than in this case. And the results were like this, that we started with 50 seconds sequential, and then actually it was almost a linear speed up with 2 nodes, 3 nodes, and then it started to be no decrease around 8 nodes or so. So it was kind of and not much difference between the methods. As I said, the parallel LB may be slightly efficient than the for each and SnowFT. Okay. We still have some time, and I have let's now first talk about summarization of this. So the parallel package contains useful tools for explicit parallel programming using the master worker paradigm, and our tools for generating random numbers in parallel environment exist, like the useR generator, and add-ons packages simplify the parallelization process and add more features. So there's the SnowFT that has all-in-one function for all the steps and dynamic resizing of the cluster. For each that defines an alternative way of loops and has convenient way of combining results and works for many different backends. And then both SnowFT and for each give you reproducible results regardless of the cluster size, including sequential runs. And that's because the streams of the random numbers are associated with tasks rather than nodes, as is the case in a parallel package. And sequential processing is possible without changing the code. As I show you on the example, right now the communication of creating nodes is time expensive, and so parallel computation is worth for larger tasks or larger number of replicates, and therefore so benchmarking is important. As a last step here, we can spend the rest of the time, there's a challenge. And so I've been working recently in statistical demography, so I got a challenge here from kind of demography area, projecting probabilistic migration, simplified version. And In this task, what we do is we know current net migration for all countries of the world. That can be taken from the WVB 2017 package, which contains the demographic or data for various demographic indicators that were published by the United Nations. And what we want is to project from current migration to future migration in 2100 with ERA1 process, and computation should run in parallel so that the countries, processing countries, is in parallel. And you can use a parallel method of your choice. And how you get the data is that you can just copy this code, and then I have a sequential version of the program. So basically, what you loop over countries, you get the migration for the country on that loop, and then you have the ERA1 process, similar to what example that we saw in the previous segment. You generate projection and for n time periods, and then return a quantile of the last point. And then I put here questions, and so I'm asking which country has the highest migration median forecast, which has the lowest 5 percentile in 2100, and then there are questions: can you reproduce the same results when running on a cluster of different size? How does the runtime differ when running on a cluster of different size? And can you explore when parallel processing gets inefficient as you decrease the number of trajectories? If you can find out, you can do it here, you can do it with a friend or something, or you can do it at home. But if you can answer these 5 questions, then you pass this tutorial. Are there any questions? Yeah.
I think all the methods and the packages you mentioned today is for one node, for one machine with multiple cores. But how to, if I want to use it in a cluster, say suppose cluster with 5 nodes, each node with 20 cores, then what is the way to do it? With MPI or?
Actually, the methods I showed is not for a single computer. It can work on any cluster, in heterogeneous cluster, and that's basically this layer that I showed you is above the physical configuration of the cluster. So you can, basically the make cluster function has other arguments that let you set a heterogeneous cluster. So, and when you have that, then you can use it the same way as we did here. Yeah, yeah. Many of you just followed, so maybe what we can do now, let's just, are there any other questions to hold, all the material that was handled?
I'm not very familiar with this term. Can you give us a difference between what is a node, the core, the threads, and CPU? I'm sorry about this, but for example, I know I have 2 cores on my machine. I have 4 threads. Should I use should I increase the number of threads or the number of cores? I'm sorry, I'm not very.
Yeah. So the physical differences between CPU and core, maybe I should ask Kirill, I don't know but I would say there's not much difference. There is physical difference, but the computers with different cores can run truly in parallel, right? But with threads, they are not. The threads kind of pretend they are in parallel, but they are not. So as you can see here, for example, on my computer, I have 8 threads, but as you see, once I'm starting to use more than 4, it starts to increase the time. So, does anybody have better answer differences between core and CPU and threads some more in detail. Okay, so.
Therefore, practically, we can trust the number of cores, not the thread.
Right, yeah. Any other questions? Yeah?
If you have multiple users on the same machine, perhaps hundreds of cores, what's the impact on how do they interact with one another given this experiment? And what's the impact on concurrency and whatnot? Do you have any guidance for how to manage that?
I suppose it depends on the software that's implemented. You probably talk like about cluster, right? Like cluster, yeah. It depends on the operating system or system that is on top of the operating system below this, right? So, for example, our departmental cluster has Slurm on it. Maybe you guys are familiar with that, which actually kind of handles the assignment of processors and memory to users. And then once you have that assigned, then this just works on top of that, right? It just uses whatever is assigned to you. So there are other like mosaics that also deal with distributing resources in some way. So these are kind of questions underneath of this. And of course, if you are sharing cluster with this, it wouldn't be a good idea to like spread yourself, on all cores and everything. It's always kind of good to be a good citizen and look the load, and for that the dynamic resizing of the cluster is helpful. So. Okay, if there are no other questions, then I would say that our kind of the official time of the tutorial is over, and so I invite everybody to stay and work on the challenge to pass the tutorial, and I'm here available for questions. Okay? Okay, thank you.